Cast is now starting. All attendees are in listen-only mode.
Welcome, everyone. On behalf of the Southern Alliance for Clean Energy, I'd like to thank you for joining us for today's webinar with a report back from the climate scientists who briefed Governor Rick Scott this week. My name is Chris Carnevale, and I'm the Coastal Climate and Energy Coordinator for the Southern Alliance for Clean Energy. Before we get started today, I'd like to take just a moment to review the basic functions of the control panel on your screen. If you'd like to minimize your control panel, just select the orange arrow in the left-hand corner and select the arrow again to display the panel. To ensure sound quality, all attendee lines will be muted throughout this presentation, but we encourage you to please type in any questions you may have in the questions box on your control panel. We will answer questions at the very end of the presentation today. For those of you not familiar with the Southern Alliance for Clean Energy, we're a regional organization focused on promoting responsible energy choices that create global warming solutions and ensure clean, safe, and healthy communities throughout the Southeast. We're a membership organization, and we would like to acknowledge our members on this call and encourage those of you who are not members to please join us today. For ways in which you can become a member and get involved, please visit our website, www.cleanenergy.org. And now, to lead us through the presentation today, I would like to introduce SACE's Florida Director, Susan Glickman.
Thank you very much, Chris. And we all know that climate change and the emissions that are coming from the burning of fossil fuels is a serious problem for the whole planet, and especially in Florida, where we are ground zero for the impacts of climate change. Because of that, 10 scientists from around the state of Florida joined together and asked Governor Rick Scott for the opportunity to brief him on the science of climate change. And that meeting took place this week, and as Chris said, we are here to report back on that. So we are going to start, and we are very fortunate to have Dr. Jeffrey Chanton from Florida State University and Dr. Ben Kirtman from the University of Miami and Dr. David Hastings from Eckerd College with us today. I'm going to introduce each one of them, and then they will give you the presentation, and it is essentially the same information that Governor Scott heard, and they're going to share with you their experience and really observations of that meeting. So first we're going to start with Dr. Jeffrey Chanton. Dr. Chanton is the John Widmer Winchester Professor of Oceanography and Chemical Oceanography in the School of Earth, Ocean, and Atmospheric Science at Florida State University. Dr. Chanton?
Yeah, hi. So am I on? Let's go to the first slide of mine. Here we go. Keep going. Next slide. Next, we're going to go to the next one. Okay, so the things that I talked to Governor Scott about was how the past is the key to the present and the future. And the way that we can get at the past, the geologic climate history of Earth, is through these ice cores. And ice cores are long tubes that are driven into the places where snow and ice are accumulating in Greenland and Antarctica. And in these situations, time is depth. So because these ice sheets are accumulating, the deeper you go, the older the material is underneath. And the ice traps little bubbles of the atmosphere as it accumulates, and so it's quite amazing. You have this continuous sampling device at the poles that's going along collecting samples of the atmosphere. And you can get the chronology or the time history of this from little layers that are in the ice. And so we have this continuous recording device that's taking samples for us. And it also tells us the temperature because of the isotopic composition of the ice itself. Next slide, please. So this is some ice core data from Greenland, where the accumulation rate is relatively rapid. And on the, you see three graphs here. Let's just look at the orange graph for right now. You see that the time history here is from the year 2000 to present, pretty much, to the year 1000 pre-industrial times. And if you look at the carbon dioxide concentration on the y-axis, you can see that it runs along at 280 parts per million until about 1800, when the Industrial Revolution began and we started to mine coal and oil was discovered, and we started using all these fossil fuels. And with that, the CO2 concentration in the atmosphere increased by about 40%, and today it's about 400 parts per million. Methane is another greenhouse gas, and you can see that it has increased 240% over the same period, the industrial era. So that's our Greenland rapid accumulation cores. Next slide, please. So look further at what the climate history of the Earth has been. We went to Antarctica, and there we got a really good record of the Earth's glacial cycles in a period that we call the Pleistocene, and this went back about 2 million years, and we have a good record for the last 800,000 years of this, or the last half of the Pleistocene. And it turns out that during this period, the Earth has had two channels. Climate has two channels, Channel A and Channel B, and it flips between these two channels on a 100,000-year time scale. Somebody's typing. Maybe they should mute their microphone while they're typing. So there are two channels of climate: the glacial state, which is in the upper Earth picture, and the interglacial state, which is warmer in the lower Earth picture. Glacial state is cold, interglacial state is warm, and I'm going to show you how the Earth's climate has varied in the next slide, please. Okay, here we see an age. On the x-axis, we go back 800,000 years, and we have three graphs on this panel. We have temperature, which we get from the isotopic composition of the ice itself in black. We have methane concentration, and we have CO2 concentration. Methane is green in the middle, and CO2 is in red at the top. Here we see that temperature has gone through these oscillations. You see that time zero, we're in an interglacial or warm period now. The temperature is warm, about 6 to 8 degrees warmer than it is during glacial times. Then there's a long period of glacial activity, and then there's another peak of temperature. I don't know if you can see my cursor moving. Who's got control of the mouse? Could you put it on those peaks there in the temperature? There you go. Okay, so go there. Each one of these is temperature. That's the temperature record. You can see the warm periods and the cold periods. And if you look up at the red line and the green line, you see that the greenhouse gas concentrations are correlated with temperature in a very significant way. So when temperature is high, the CO2 concentration reaches 280 parts per million. That's what it was in pre-industrial times in the Greenland cores. And when temperature is low or cold, the CO2 concentration is about 180. So we see that for 800,000 years, there's a very tight correlation between temperature and carbon dioxide concentration. These two things run together. There's no doubt about it. Now, if you look at the far right corner of the graph, you see that the CO2 concentration is going off the scale. It's up to 400 parts per million now. And this explains the warming that we observe in the ocean and in the atmosphere and the melting of the glaciers that we are currently observing. Because the CO2 concentration has gone to 400 parts, we might expect our temperature to go up as well. And most significantly for Florida, as the temperature and the CO2 concentrations move up and down through these glacial to interglacial cycles, warm and cold periods, sea level is changing significantly as well by 300 feet. So during the warm period, sea level is 300 feet higher, and during the cold periods, it's low, 300 feet lower. Okay, so it's going up and down by 300 feet. And that's because when you melt the glaciers, that water runs into the ocean and raises sea level. And when you warm the oceans, the water expands and it takes up more room, okay, because it's less dense. That's called the thermal expansion of seawater. And so the sea level is going up and down with CO2 concentration, as is the temperature. Okay, these three things are tightly correlated. So as we go up to 400 parts per million, we experience higher temperatures and greater sea level rise. If you go to the next slide, please. Here we see just the CO2 concentration for the last 400,000 years. Zero is on the right side on the x-axis going back 400,000 years. On the y-axis on the right, we see the CO2 concentration. And it's quite amazing to me that CO2 concentration at the interglacials, the warm period, it goes up to 280 and stops there, and then it goes back down. During the cold period, it gets as low as 180. And then the last graph we saw it for 1,000,000 years. CO2 has varied between 280 and 180 parts per million. It has not gone outside those bounds. Now it's at 400 parts per million. And by the year 2100, if business continues as usual and we continue to burn fossil fuels at the projected rate or even at the rate we're doing it now, the CO2 concentration will be up to 700 parts per million, which has not been experienced on the Earth for millions of years. And when it was that high, the climate was significantly warmer and sea level was a lot higher. Okay, so this is why I think it's so clear that there's a linkage between CO2, sea level, and temperature. Okay, and our next speaker will elaborate on that further. Thank you.
Very good. Thank you, Dr. Chanton. And next, we're going to hear from Ben Kurtman. Ben is a professor in the Department of Atmospheric Sciences at the Rosenstiel School of Marine and Atmospheric Sciences at the University of Miami. Dr. Kurtman?
Thank you, and thank you, Jeff, for that very nice discussion, and thank you all for attending. One of the things before I launch into talking about the science, I did want to take a moment to just explain why I personally participated in this process and wrote the letter to the governor and feel committed to this enterprise. And to me, it really comes down to something very, very simple and straightforward. The science of climate change is very robust. It's solid science, and we need our policymakers and our politicians to acknowledge that, so that communities and cities are empowered to develop adaptation strategies for dealing with a changing climate. When our leaders deny that it's happening, it makes it very difficult for communities to figure out how to respond, because someone at the top is saying, oh, don't believe in it. So local communities have to deal with the problems associated with climate change in the very near term and also in the long-term future. And so, you know, we can disagree on what the right policy prescriptions are, but we should stop disagreeing on the science. And so let me just begin by demonstrating to you what I think is compelling evidence of why climate change and science is solid, and that it's unequivocal or very clear that human activities are in fact affecting climate. And so as part of that, what I'm going to be showing you are results from two enormous enterprises that involve the best scientists in the world. The first one is called the Intergovernmental Panel on Climate Change, which I'm sure a lot of you have heard from. And these are the best scientists that are studying climate variability and change. And the second is a parallel process. It's called the National Climate Assessment. And those are scientists from the United States that are really studying the problems very carefully on a much more localized level. And so these results that I'm presenting you, it's a little bit like the AMA of climate science. This is truly tested, stood the test of time in really large, multiple lines of evidence in all of these statements that I'm gonna give for you. Okay, so this first slide on the left-hand panel, I'm showing you modern instrument records. The very top is land surface, air temperature, and the details here, there's so many panels here, I don't want to go into the details. I just want to point to this overarching notion that there are multiple lines of evidence. So you can see this is a temperature, the top one is a temperature record from 1850 to the present. And you can see there are 4 different data sets, and they're all pointing to the same thing, that the climate system has warmed since the 1950s, and that is unequivocal. You see that in the sea surface temperature data sets. In this case, there's 5. Marine air temperature, there's 5. With the sea level record, we have 6 different data sets, all pointing to a 10-inch increases in sea level pressure since the late 1800s. One of the most important ones is this bottom one. This is Arctic sea ice extent. Now, Arctic sea ice extent is really important because one, it's a little bit of a canary in a coal mine for us. It has a very slow process, so it's really an integrator of climate change. And the other part of it is, as it melts, it also actually changes how much solar energy reflects from the Earth. So if you start to lose sea ice, the oceans are actually, and the poles are able to absorb more heat. So as we lose ice, we're actually contributing to a potential acceleration of global warming. So that Arctic sea ice is really an important indicator. The right-hand panel is another one that I consider to be really important. And what that's showing you is just how much heat is being taken up by the oceans in comparison to the atmosphere largely. And so you can really see that we've locked ourselves into a certain amount of warming because the oceans have continued to warm, and there's no signs that any of that is going to slow down. So there's this continual heat uptake that's happening in the climate system, and so we are sort of guaranteed to some near-term climate changes. Next slide, please. Okay, so that was the modern instrument record, and what I want to do now is I want to just focus on one element of that modern instrument record, and that's the global mean surface temperature. And we can do this analysis with every single one of those data sets. We can attack these multiple lines of evidence with each one of these data sets. And on the left-hand side, what I'm looking at here is a separation of all the processes that affect climate, that affect global mean temperature. So the top panel is just the observed record of temperature. The second panel is how a very well-known process contributes to that global mean temperature. And so that second panel that says ENSO on it, that's El Nino and the Southern Oscillation. So that's that warming in the tropical Pacific that happens every 3 to 7 years that we're all quite comfortable with. The third panel, the one that's labeled C, that's volcanoes. Volcanoes are actually a cooling of the climate. So you can see volcanoes, when a volcano goes off, that cools the climate system for a year to, say, 18 months, maybe 2 years. D, that's an important one. That's the solar, right? And so you can see the 11-year solar spot cycle. You can see how solar irradiance has affected global mean temperatures. And all three of these so far I've shown you are pretty small. They're pretty small numbers. And then if I go to F, I'm skipping one for an obvious reason. If I go to F, that's other modes of variability that we know about. And climate modelers and climate scientists, we have a name for every one of them, and there's a half a dozen of them. But you can see that's how much of the temperature record that those other modes of variability explain. So the big one, the elephant in the room, is the one with the black oval on it. That's the CO2. That's the anthropogenic forcing that comes from human activities. That's the burning of fossil fuels. That's that part of the temperature record that's explained by increases in carbon dioxide. And so that's the fingerprint, if you will, of human activities on the global mean temperature. That's very clear that human activities have affected climate since the 1950s. We can do the same thing. That's just a raw data analysis. We can do the same thing with our best available climate models. I can take apart each bit: greenhouse gases, solar, ozone, volcanoes, other forms of pollution, all of those other elements. And that's what the panel on the right-hand side is showing. And you can see very clearly with the blue curve that the temperature record, we cannot reproduce the temperature record if we do not include the human pollutions associated with greenhouse gases. So that's the only way we can recreate that observed record. So again, this notion of multiple lines of evidence, that this is not just one modeling study, this is worldwide, great deal of models, great deal of data analysis that really point to robust science that increasing greenhouse gases has explained the warming that we've seen since the mid-century. Next slide, please. And so my last point here is sea level, and this is a sea level plot sea level projection plot from the National Climate Assessment. And so this is, of course, most relevant to us here in Florida. And it includes, several projections. The gray curve is a lowest projection, if you will, a continuing of the trend. The yellow curve is from the IPCC report that came out in 2007. The orange curve there is for the IPCC report that just came out in September 2013. And then the red curve is yet an even higher assessment based on some additional studies. So these are all projections. They all have uncertainties associated with them. At the moment in time, we're not able to put probabilities on any one of them, and we can't put probabilities on any one of them because they're dependent on human activities. So these projections out to 2100 for sea level rise depend on what we decide as society to do with burning of fossil fuels. So some of this is it's not just the climate system running amok. This is human activities are going to determine what the future sea level rise is going to be. So we're at an important moment in time here. The inset here is meant to be helpful to interpret those projections. To help you interpret those projections. So that gray box there on that plot is actually what came out of that 2007 IPCC report. Those were the projections of what sea level would look like. Okay, so it includes that gray wedge includes the very lowest from the IPCC and also the very highest from the IPCC. The red curve on that inset, that's the tide gauge data. That's what we actually have, and the blue is from satellite observations of what actually happened with sea level. Okay, and so you can see why the IPCC report, the AR5, the more recent one, went to slightly higher projections, and why even more recent reports from the National Climate System go to even higher projections, because we seem to be on a trajectory that's sitting on these higher projections. Now, again, the future to 2100 depends on what we do today in terms of burning fossil fuels. What's going to happen in the next 10, 15, 20 years, the projections for sea level, we're guaranteed a certain amount of sea level rise. It's already built into that ocean heat content, because as those oceans warm, the ocean expands thermally, and sea ice continues to melt. Ice sheets on land continue to melt, and that puts additional fresh water into the ocean, and so the sea level will rise. So we can't stop it for the next 10 or 15 years. We are committed to a certain amount of sea level rise, and so we need to adapt, acknowledge that climate is changing, and we also, at the same time, we need to start thinking about how we're going to mitigate the long-term future. And I'll stop there and turn it over to David.
Very good. Thank you, Ben. So next we're going to hear from Dr. David Hastings. Dr. Hastings is a professor of marine science and chemistry in the Galbraith Marine Science Laboratory at Eckerd College.
Good morning. What a pleasure to talk to everybody, whoever you are out there in the digital world. I want to just step back a minute and just give you some context for why I'm interested and engaged in this. I'm a paleoclimatologist, so I study the history of climate over geological periods, what Dr. Shanton was talking about, and I tend to specialize in the last 10 to 20,000 years or so, when there was substantial and significant rapid climate change that was due to natural causes. And as with my colleagues, I recognized about a decade or two ago that it wasn't appropriate for me to just simply sit in the lab anymore, that there was a moral obligation for me to get out and start communicating to non-scientists about the concerns that I had about climate change. And I had some insight to it fairly early on, looking at this data and appreciating the severity of it. And so now, as with many others in the scientific community, we're beginning to understand how important it is to reach out and not just talk among ourselves, but to address the larger community who are voters and citizens, and also people that are going to be affected by the impacts of climate change. I also want to point out that I believe very strongly that this is not a partisan affair. There's no reason for Democrats or Republicans associated with one position or the other. I think it is partisan at this point, and I think that's very unfortunate. So let me just briefly go over what we've determined, just to kind of summarize to some extent what my colleagues have said, was that it is in fact happening now. The climate is changing. We know that temperatures are rising, sea levels are increasing, and oceans are becoming more acidic. And we also know, as Ben pointed out, that we are causing it. While there were natural changes in the past, these changes that we're experiencing now and that we'll see in the future are certainly due to human influence. And there's an enormous amount of certainty on there, and there's a broad consensus in the scientific community. It's really unprecedented. 97% of those of us who are actively publishing in the climate change literature agree that the climate is changing and we're responsible. And the other aspect of this is that we don't have a lot of time. We have to act soon, and if the more action that we take, the sooner, the better off we'll be. And finally, the important part is that, in fact, there are solutions to the problem. This is not the impacts are not predetermined. We do know that there will be some impacts. There will be some sea level rise. We've already experienced it, but the degree of the impacts depends on what we do. And that's in fact why we went and talked to the governor, because we wanted him to understand the science. We wanted him to understand the severity of the impacts. And also, it turns out that the state of Florida has quite a responsibility here. If you can go to the next slide. The EPA, the next slide please, thanks. The EPA has developed their Clean Power Plan, and what that means is each state has a particular responsibility to lower CO2 emissions in the next 15 years. Our commitment, we've been tasked with reducing CO2 by 38%. That's a lot. This is not. This will take some planning. This will take some work. This will take considerable thought. And what we were there to ask Governor Scott is, how is the state of Florida going to meet this requirement? How are we going to go about doing it? And we were hoping and asking that he should develop a transparent process, so we actually know what he's doing. That process should be transparent. The process to develop and then implement the plan to reduce carbon emissions. Of course, it needs to include everybody. All the stakeholders who are involved need to be included. So the costs for not taking action every year increase with every year as the sea level rises. The streets in Miami are flooded. Our fresh drinking water is contaminated by rising seas and the salt water. We're seeing increased intensity of storms. Coral reefs are dying off that tourists love to visit. So these costs are substantial. But the good news is that solutions are close at hand. We know that losses can be reduced substantially by using mitigation strategies that are based on the best available science. So as scientists, we know what's possible. We were hoping that Governor Scott would be interested in how to actually do this. And there is no one single thing that he would be able to do that would reduce CO2 emissions substantially. There needs to be many different parts of the plan. One part is to eliminate coal-fired power plants. Coal-fired power plants generally tend to be quite inefficient, and we do know that they're the largest source of human CO2 emissions. So we need to reduce, or in fact just shut those off. There's lots of other sources of electricity. And one of the fastest and least expensive way to meet CO2 reductions is to simply increase energy efficiency. Our systems tend to be quite inefficient because historically energy has been inexpensive, and we haven't cared very much about energy efficiency. But just as we can drive more or less efficient cars, we can have more or less efficient power plants. So we're hoping that he would develop strong efficiency goals. And then another way to reduce these CO2 emissions is to advance renewable sources of energy. We live in the Sunshine State. There's lots of sun. We all know that. It's one of the reasons we like living in Florida. And these solar power, the price for solar power, the costs have come down remarkably. It's just they're now competitive with our more traditional sources of power. We know that Germany produces as much as half their electricity from solar power. And why not here in sunny Florida? So, you know, what we've done in the scientific community is produce this map. We describe the territory, show where the hills and valleys, the rivers, the mountains, the roads are, and the different scenarios for CO2 reduction. The governor, of course, is, along with his staff, they're the navigators. They're the policymakers. They're the ones who choose the best route and how to get to where we need to go to. So it's clear, the science is very clear, and we're hoping with the map that we provide him that he can travel a good route to get there. And what we were, excuse me, that's my other phone. What we were hoping is that he would provide some clear leadership in setting a new path. So I appreciate your attention, and I look forward to, with my colleagues, hearing some questions that folks out there have. Thank you.
So we actually already have a couple questions, and I want to remind everybody on the webinar to go to your control panel and type in questions. I have a couple on the science, but before, Dr. Hastings, this is just sort of relevant to the comments that you just made. And did you hear that the governor said yesterday at a press conference when he was asked about the meeting with you all, I'm not an expert, but? And do you have any remarks on that after actually spending some time in that discussion?
Susan, is that a question for me?
Yes. I picked up on what you were saying earlier, and then I'll go back to some of the more science questions.
Well, his role as the navigator, as the captain of the ship, is to collect the information and with his staff and develop a plan. He does not need to be an expert, but this is part of his job, is to develop plans to reduce CO2 emissions. This is simply part of his job description.
Very good. So this would be for Dr. Chanton. Can you elaborate a little bit on the effects and the correlations associated with the exponential increase of methane in our atmosphere?
Okay. Methane is a greenhouse gas. It's about 25 times as infrared active as CO2, and it's currently increasing at a faster rate. Since the pre-industrial era, it's gone up 240%. Methane's concentration, however, is only about 2% that of CO2. So even though it's a stronger greenhouse gas, it's much less concentrated. And currently, of the extra forcing, the anthropogenic forcing caused by the greenhouse gases emitted by humans, methane is about 25% of the effect of CO2. Okay, does that answer the question? Methane comes from landfills, it comes from mining natural gas, it comes from mining coal. The fracking is an issue for methane because when they harvest this natural gas, there's a certain amount of it that's spilled. We don't really know how much of it's being spilled right now. It could only be from anywhere from 0.5 to 4%, and it's a very difficult thing to measure. So that's about methane. It also comes from landfills. That's pretty much controlled, and cattle feedlots is a big source of methane.
So Dr. Kirkman, we have another question. Do you have a good understanding of the emergent properties that are associated with the joint interaction of the different processes you identified as contributors to climate change?
I I'm going to try to interpret the question a little bit, and hopefully I'll understand it correctly. So what I think is being asked is, do we understand how the natural variability processes necessarily interact with the forced climate response? So if that's the question, in some aspects we do, in some aspects we don't. So it's a very important question. So El Nino is a great example of a particular process that we are still not sure exactly what's going to happen with El Nino in a changing climate. Some of our tools tell us that El Ninos are going to be larger and or maybe even more frequent. Some of our tools tell us that El Ninos are going to be weaker and less frequent, and some of our tools tell us that there's going to be no change at all. So while we understand the source of the trend and how that trend affects, there are elements of the climate system where we still have to solve problems. El Nino is being one. We've made great strides in understanding how extreme weather events are affected by a changing climate, but we also have a great way to go. There's lots of things we need to understand about regional sea level rise as opposed to global sea level rise that is affected by ocean circulation, if you will. And so there are definitely still open science questions associated with climate change, despite the fact that there are elements that are settled science. So there is, and that's the nature of science. There are, things that become settled and elements that remain open questions.
Very good. So the next question comes from Lindsay Abrams with Salon, and she is appreciating the great refresher course for all of us. I'm sure we all feel the same way. I learn something every time I hear these presentations. Did Governor Scott ask any questions during the presentation?
Is that for me?
Well, go ahead, Ben, and you can each respond if you feel the need.
So he certainly he chatted with us and he asked a couple of things, but I think the environment that we were in made it very difficult for the governor to the amount of time we had. And in all honesty, the presence of all the press made it difficult for, and the governor did not ask questions that delved into the understanding of the science. So he really didn't take that opportunity to engage with us under the discussion of the science. And so if the governor's office is listening, we would be willing to try again, I think, to really engage on understanding the science.
And we have a additional question asking, do any of the scientists think that Governor Scott sort of got it? Does he actually get it? So maybe Jeff Chanton, would you want to take that question? Do you think he actually got the science?
Well, I expect that he got something out of it. It's a lot of information was thrown at him in 20 minutes, and so I can't expect anyone to have absorbed all of that in 20 minutes. But I'm sure he gleaned something out of it. And as I said before, I really hope that he will consider learning more about this. It's a fascinating subject. One of our party gave him a book on sea level rise to read, and I hope he reads that, and I hope he gets behind this in a big way. Thanks.
Very good. And then another one of the questions is, did the governor state if he had a plan to address the reduction of carbon pollution, and would there be some sort of task force formed to address this? I guess Dr. Hastings?
Right. This would have been an excellent opportunity for him to have talked about what he's going to do either now or in the next few months about how he needs to respond to the EPA Climate Action Plan. It would have been a good time for him to have talked about what his understanding is and how the state is going to move forward. And in fact, he didn't respond at all to either the science or to our request for him to address how he's going to move forward.
So we have another science question. Dr. Chanton, can you explain a bit more about the 300-foot sea level rise, lower and higher depending upon the temperature and the thermal expansion of seawater, and how does this fluctuation affect coastal resiliency?
Well, the 300-foot temperature rise was accompanying the glacial to interglacial transitions. So during glacial periods, we had glaciers that came all the way down to New Jersey, and there was a lot of ice or a lot of water stored on land as ice. And so as those glaciers melted, water was transferred from the continents, from the land to the sea. And so that during the glacial maximum period, sea level was 300 feet lower than it is today. And like the West Florida shelf, the on the west coast of Florida, on the Gulf Coast, the shelf is very shallow, and all of that was exposed out to the shelf break. The shelf break is a feature that separates the continental shelf from the continental slope. And so the coast, the place where the ocean meets the land, was all the way out at the shelf break during the height of the Pleistocene glacial periods. And then during the interglacials, the sea level was about 300 feet higher. Now, right now, as sea level rises, it's due about 50% to the thermal expansion of seawater and 50% to the melting of current land on, or ice on land. 50-50. Thermal expansion, ice melting on land. And the thermal expansion is explained as if you've ever been to a lake and you jump in the water in the summer and it's really, really nice and warm on top and it's cold underneath that. What you're experiencing there is that the warmer water is less dense than the colder water, and so it floats on top. And by less dense, that means it's expanded. So when you heat water, it takes up more space. And so both those things are contributing to sea level rise today.
Very good.
Yeah, probably in the interglacial to glacial transition, it was mostly the melting of ice on land, although both things were responsible.
Very good. So we're also being asked, will the replacement of coal-fired power plants by natural gas have an effect on climate change?
I can answer that. It does have an effect. When you burn coal, you produce more CO2 for every amount of energy that you produce. So coal produces the most carbon dioxide because it produces a lot of water as well. When you burn the hydrogen on the methane, you get less CO2 for a unit of energy. So burning natural gas produces energy more efficiently in terms of CO2 production. The thing about natural gas is, as you mine it, you have to be very careful not to spill it to the atmosphere. During the 1980s, the methane concentration in the atmosphere was rising very rapidly, about 1% per year. And it was an incredible mystery what was happening at that time. And then when the Soviet Union fell, the Western oil companies went into the Soviet Union and they found that the pipelines, the natural gas pipelines in Russia were made of cast iron. And another component of natural gas is hydrogen sulfide. That H2S, hydrogen sulfide, was being oxidized, forming sulfuric acid and eating away at the pipelines of natural gas in the former Soviet Union. So when those pipelines were replaced, the rate of methane increase in the atmosphere slowed considerably. So good policy in the mining and control of natural gas is very, very important.
Very good. Does anyone else want to respond to that? So
yeah, I'll just weigh in briefly because, of course, fracking is a very large concern. We're getting a lot of natural gas from a lot more than we thought was there, and this is a cleaner source of energy than coal. And what Dr. Shenton is pointing out is if we extract it without any good regulations and without any good understanding of how it's leaking, and it's hard to, we need to pay attention to how we're extracting that natural gas. And at this point, we are not paying good attention to the natural gas leaking out as we extract it from the earth. And we just need to pay much more attention because it's a very powerful greenhouse gas. It's 20 or 30 times more effective than carbon dioxide. So really the low-hanging fruit here is to reduce methane emissions, and we certainly don't want to be leaking more methane into the environment.
Very good. So one of the questions being posed is the position around the expanding nuclear energy production as part of a solution to reduce carbon emissions. And I would just mention that there's only one proposal in the state that currently to do that at the Turkey Point, and one of the scientists who was with us in the meeting, Harold Wanless, who's not on the phone today, has a particular area of study around sea level rise and that issue. So is there anyone that wants to sort of address that, and in particular, because that's what the governor and the Florida cabinet voted to certify in the nuclear plants in Turkey Point, which is and in the order was only preparing for 1 foot of sea level rise. So anyway, I throw that out there. Someone would like to respond to that.
Yeah, I'd be happy to do that, and then my colleagues can follow up. Nuclear power is very appealing because there's little CO2 emissions from it, and so it's a very attractive source of energy at this point as our concern with heat-trapping gases becomes larger and larger. The problem with nuclear is that it's really not on a level playing field with regard to costs. So because it's so heavily subsidized, if we level the playing field with regard to costs, then nuclear becomes much more expensive, and then renewables become very, very good sources of energy and electricity because they're such a good value. So again, nuclear is attractive because there's no little CO2 emissions, but we need to recognize how incredibly expensive these nuclear power plants are and how much they're subsidized. So what I would argue is that we need a level playing field, and then the renewables that just become the first option.
Dr. Kurtman, do you have just any sort of sense of the sea level rise issue, and what does that mean, obviously, to the not only existing nuclear plant, but also the millions of pounds of nuclear rods that are sitting in pools there, in terms of just the sea level rise aspect?
Well, I'm certainly not a nuclear power plant expert, but I do know that the best available projections of sea level rise over the next 5, 10, 15, and even 25, 35 years were not being used in any kind of planning decisions, and I really think that's the one element of the heart of the problem, is that in all of these energy decisions, infrastructure decisions, Everglades restoration, Turkey Point, whatever it is, we need to actually engage in and make sure the best available science is informing our decisions of how we build these things and how we modify these things. And I know they didn't do that with Turkey Point, and I'm not a nuclear expert, so I don't know precisely what the risks were, but they should have included that in the risk assessment in deciding how to go forward with the plant.
Very good. So we'll go to another sort of solutions-oriented question. And you're being asked if you've heard about the sort of revenue-neutral carbon fee and dividend scheme, which encourages reduction in carbon use as well as development of alternative energy. So it's a carbon fee as opposed to capping emissions and trading them. So cap and trade, carbon fee. Is anyone familiar with that?
Yeah, I can speak to that. I think that that's a really, really good idea. It's revenue neutral, so it returns the money to the people that spend the money. But what it does is it makes fossil fuels proportionally more expensive. So you might be paying more money for fossil fuels. You'll be getting the money back, but they'll take a larger part of your budget, and so they would discourage your use in that commodity. So I think that the carbon fee is a brilliant idea, and I am totally behind that.
The challenge, of course, is that when we put greenhouse gases, CO2, methane, all these heat-trapping gases into the environment, we're not paying the costs, the environmental costs of it. And we need to somehow reflect those costs, because there are real costs with putting CO2 and other pollutants into the atmosphere, and those are not reflected in our economic system. And so if we want to stay on the planet for a while, we need to incorporate this, and market-driven responses are a really effective way of doing that. We don't put raw sewage onto the street the way we used to, and there's a reason why. It's because it smelled, and
Yep.
unfortunately, CO2 doesn't smell the way raw sewage does. But we need to treat these pollutants in the same way and treat them seriously.
That's right. The atmosphere is the only place where we freely dump our waste without any charge. And that's the worst place to dump waste because that is the thinnest, most dilute reservoir of all. Between the hydrosphere, the lithosphere, and the atmosphere is the most easily affected.
Very good. So we have about 4 more questions, and we'll get to those pretty quickly here. So we're being asked if you can give some specific examples around Florida of climate change and sea level rise already having an impact. Dr. Kurtman, that's probably up your alley.
Yeah, sure. I can comment on that. So, the best example I see on a regular basis is here in South Florida in Miami Beach, where the frequency of what they call clear sky flooding events, that is, there's no rain at all, but the sea just comes into Alton Road in Miami Beach and floods it. These clear sky flooding events are now becoming much more frequent, and that's entirely because of sea level rise. So during high tides, particularly, there's 2 high tides every day, and so the highest high tide we call the high tide. That during that tide, during October, Miami Beach is particularly vulnerable for these clear sky flooding events, and they've become decidedly more frequent in the last 5 years or so, and they're going to continue to rise. So, enormous construction projects in Alton Road, stormwater management systems have to be invested into, and that's becoming a real challenge for that local community. And if we say there's no such thing as sea level rise or no such thing as climate change, it makes it very hard for that community to rally to solve this problem. And they can solve this problem. Another example of sea level rise, again, in South Florida, is the saltwater intrusion into freshwater aquifers. So as sea level rises, the saltwater starts to penetrate into the freshwater aquifers, and that has a limiting effect on our freshwater supply. And you have to start thinking about some pretty expensive solutions to that problem that include desalination of wells and things like that. So a sea level rise is a problem today, right now in South Florida. We're extremely vulnerable here, and if we don't acknowledge the problem, we certainly can't fix it. And so I agree with David's fundamental statement. This is not a partisan issue. This is a problem that we face. I'm extremely optimistic we can fix it, much like David and Jeff also. We can fix this problem. We just acknowledge it and get to work on fixing it.
Very good. So another substantive question, Dr. Chan, do you believe fracking is coming to Florida within the next 5 years? Are you following that, or any of you?
Do I believe, excuse me, I didn't quite...
Fracking, the hydraulic fracturing.
Yeah, what about it?
Just that it's going to be happening in Florida.
It seems like it might well be. It's quite amazing to me how much natural gas is present in the subsurface of the Earth. And there's older oil fields in Florida, the Sunnydale, and it seems that fracking is a way of extracting additional energy from these old, worn-out oil fields, and so it seems quite likely that there will be fracking here in Florida. Yes.
And
So,
I'd like to add on just that the acid fracking, using acid to dissolve the limestone, this is a whole nother level of concern, and I think this should be avoided at all costs. To dissolve the carbonate to get out this methane is there's really no reason to approach this this way. This is extremely harmful to environmental systems.
So we're gonna I'm gonna just ask 2 more questions here, and they're somewhat interrelated. So one of the listeners is asking if you would consider an audience with Adam Putnam, who is our Commissioner of Agriculture, and the Department of Agriculture and Consumer Services actually houses the State Energy Office, so he has a lot to to say about energy, was the one who actually made the motion to certify that the nuclear with the sea level rise issue. So would you consider a meeting with Adam Putnam?
Delighted.
Absolutely. Okay, we have delighted. Okay, so we'll look to do that. And then,
of course.
Yeah, good. So why don't we wrap up with this last question, and I'll let each one of you answer, and why don't we do it in the same order which we presented, Dr. Chanton, Dr. Kurtman, and then Dr. Hastings, which is, are you frustrated as scientists? I guess with, and we don't need to limit it solely to the governor's response, but to the response of policymakers, in particular the governor, but are you frustrated?
Yes, I've been very disappointed with the traction that this issue has gotten over the years. I've been pretty concerned about this since the 1990s, and it's just amazing to me how little attention has been paid to it and how much misinformation has been put out by various entities. So it's been frustrating, yes.
Great. Dr. Kurtman?
Yeah, I'm extremely frustrated. I do think this politicalization of science, the best available science, is a very dangerous precedent. I think all of our decisions need to be informed by the best available science, and when we fail to do that, I think we can't have a robust and honest policy debate about what are the costs of doing something versus the losses that would occur due to inaction. And so to really be economically sound, we need to use the best available science to inform how we do things. And I'm very frustrated that we're not doing that.
Okay, Dr. Hastings, and then we'll wrap up.
Well, it's good to have unanimity on this. In fact, scientists are, there's a tremendous amount of consensus, and I concur with both of my colleagues. And yet, sometimes when I need a break, I swim in the ocean or I go walking in the woods. And in a similar situation, sometimes I go to Seattle or Portland or go to Europe and see what they're doing there. And it's tremendously exciting to see how different communities are moving forward. The actions that are going on in California, Oregon, Washington State, New England, and especially Europe, these are extremely exciting and inspirational. And I take inspiration from other communities that are moving forward and that provide me with a tremendous amount of hope that it's not a done deal and that actually we can fix it. So I remain hopeful by going and seeing what other folks are doing and hoping we can do it at home as well.
Very good. Well, I want to thank you all, Dr. Hastings, Dr. Chanton, and Dr. Kurtman, for doing what you're doing and leading, and I appreciate everyone also being on the call. Turn it back over to Chris. And
thank you, Susan, for what you do as well.
Certainly.
And I just want to echo that thanks. Thank you, Drs. Chanton, Kurtman, and Hastings, and also thank you everyone who's on the line for joining us today and also for your thoughtful questions. For more information, please check out our website, www.cleanenergy.org. Today's presentation has been recorded and will be available on the webinar archive page of our website. And we will send you a link to the recording once it's been processed. We appreciate your support and interest and hope that you'll join us again. Thanks again. Bye.
Thank you.
Bye-bye.